The most common cause of failure for a cylindrical steel stack is wind-induced vibration, which is often referred to as vortex shedding. Vortex shedding is a very complicated subject, and we would encourage you to go to our website and search the articles section for vortex shedding, where you will find some more in-depth discussion on this complicated topic. Every structure has a certain amount of inherent structural damping that will help diminish the effects of harmonic vibration on a structure. The structural damping has the biggest effect on the structure's sensitivity to vortex shedding. There are many factors which contribute to the structural damping, such as the type of connections, materials being used, soil, foundation, etc. We don't often know all of these details when designing the structure, and even if these details are known, the only way to really accurately determine the structural damping is to erect the structure and perform testing. This is obviously not practical or economically feasible in nearly all situations. The practical approach is to use conservative guidelines to estimate the structural damping based upon past real-world tests that have been performed and documented. That brings us to the damping menu, which is where you can specify the structural damping. At the top of the screen, you select the criteria, which are some industry-recognized standards for chimney design that have some predetermined values for structural damping based upon some general information about the stack. For example, if I select STS, then the two questions are whether the stack is lined and the type of foundation. Based upon these two entries, the structural damping is automatically determined and shown in the grid below. If you feel you can best enter your own structural damping value, then change the criteria to manual and you can manually specify the structural damping. The next entry is the criteria to be used for the aerodynamic damping. Aerodynamic damping is a more complicated topic than we can cover here, but in layman's terms, it is damping that can contribute to your stack for along wind loads, which are the wind loads used to design the stack for the design wind speed. However, aerodynamic provides no help for across wind loads, which would be vortex shedding. Select the aerodynamic damping method that matches the standard you are using, and if your standard isn't available, then you can pick whichever is most closely aligned. The air density is used for some of the wind and vortex shedding calculations, and a value at sea level is the default. Next, we will skip down to the number of modes entry. This will determine how many modes are considered in the analysis. Typically, this would be 3. Within the grid, you have the option to override a frequency by checking the box. This would be used if you had a stack supported on a structure, and the combined frequency of the stack and structure was different than that of the stack supported on a rigid foundation. Similarly, you can also check the override damping box to manually enter a structural damping value for any of the modes. In many cases, the stack's inherent structural damping is not enough to suppress vortex shedding, and your stack is being controlled by it. This is when we might need to add something to our stack in order to address this vortex shedding problem. These additional items are included in the damping device menu. The first option you could pick are helical strakes. These are typically placed on the top 1/3 of the stack, and they are vertical fins that wrap around the stack in a helical pattern. They aren't really a damper, they actually work by disrupting the vortices from forming in an aerodynamic manner. Helical strakes do have their limitations and disadvantages, and we have articles on our website that discuss this in more detail. Next, we have 3 different options which will increase the structural damping for the stack. We have articles on our website that discuss these in more detail, and so we will just discuss these from a high-level perspective. The damping pad is a pad that goes under the base plate for the stack, and there is a damping washer for each bolt. The tuned mass damper and tuned liquid dampers are both engineered devices that are placed near the top of the stack. Meca provides all of the damping solutions mentioned. Simply selecting the damping option on this screen does not design the damping device, it only accounts for it in your analysis. For example, if you select a tuned mass damper, you can specify some basic dimensions and weight for the device. This will be used to represent the damper graphically in your model, and will account for its weight and wind area. However, the most important aspect of the damper is the amount of structural damping that it provides. In order to get the structural damping, you would need to email Meca your input file, and we size the damper and perform an estimate, and then we return it to you with the estimated structural damping provided. For any of the dampers, this is the usual procedure. You are designing your stack and you find that vortex shedding is a problem. You can turn off the vortex shedding by manually specifying the damping value as being relatively high, which is usually about 0.02. Then you design the remainder of the stack to meet the other design loads. Once you get the stack as you want it, then you email us the file. We then take that file and design the damper and return the file with those damper parameters entered into the file. The damping value you use will have a huge impact on the structure's response to vortex shedding. If you arbitrarily make the value higher so that you avoid a problem today, the ultimate test will occur when it is in the field. If you are too optimistic with your damping value, then the cost will be much higher to rectify when it's in the field, and you get a phone call indicating that the stack is swaying in the wind, or even worse, that the stack has failed. We urge you to always be conservative with your damping estimates. It's not worth the risk.